Hello everyone, today we'll be discussing our work on Apache Spark SQL. This is a critical step towards making big data processing more efficient and predictable. Our presentation will cover why cost models matter in distributed computing, the limitations of current systems, and how we extended existing research to validate and test Spark SQL's performance predictions.
Let's start with the challenge. As data volumes explode over the past decade, traditional database systems simply couldn't keep up. They were designed for smaller, centralized environments. This created an urgent need for scalable frameworks that could handle massive datasets effectively while supporting both analytical queries and complex procedural operations.
Apache Hadoop was the first major breakthrough. It introduced MapReduce, which allowed parallel processing across clusters. However, MapReduce had serious limitations. It required low-level coding, which was slow due to constant disk writes and made development both time-consuming and error-prone.
Apache Spark changed the game. It kept Hadoop's fault tolerance and scalability, but added in memory computation and pipelining. This meant data didn't need to be written to disk constantly, resulting in performance that could be orders of magnitude faster. Spark also became a unified engine supporting machine learning, graph processing, and streaming all on the same platform.
To make Spark more accessible, especially to users familiar with SQL, Spark SQL was introduced. It allows standard SQL queries to be automatically translated into Spark commands and executed in parallel across a cluster.
At the heart of Spark SQL is Catalyst, an optimizer that breaks down SQL queries, applies rewrite rules, selects execution plans, and generates runtime code. Catalyst bridges the gap between declarative SQL programming and procedural RDD-based operations, making Spark appealing to a much broader audience.
Here's a problem. Despite Spark SQL's popularity, its optimization capabilities remain limited compared to traditional database systems.
Catalyst uses rule-based optimization, meaning it follows predefined patterns to rewrite queries. But unlike traditional databases, Spark SQL lacks a robust cost model that can predict how long a query will actually take to run.
Traditional DBMSs rely heavily on cost models to choose the most efficient query plans. Spark SQL doesn't have this capability, especially when accounting for distributed execution, network bottlenecks, and Spark-specific behaviors. This gap is significant because accurate cost estimation is crucial for query runtime, prediction, cluster planning, and building a truly cost-based optimizer. Our work builds on two key research papers. The first, by Baldacci and Galfrelli, presents the first analytical cost model specifically designed for Spark SQL. It covers a wide class of queries modeling three basic operators: select, join, and generalized projection.
The second paper on Spark SQL explains why this cost model makes sense, showing how Spark SQL enables users to mix relational and procedural programming, and why SQL support is essential for optimizing modern data pipelines. Our goal was to replicate these cost model results and extend them by testing on a new dataset. This allows us to access Spark SQL's scalability and explore potential optimizations.
Views in Spark SQL so I could execute SQL queries directly over the relations. Spark loads these files lazily, so each time a query runs, it goes through Catalyst optimizers, applies logical and physical planning, and generates the execution plan. I recreated each view, customer, orders, and line item with the appropriate schema, including the correct column names. With the views ready, I was able to run the TPCH benchmark queries. For Q1, Spark SQL ran in about 0.497 seconds, while the RDD version ran in 0.025 seconds. This difference occurs because Q1 is embarrassingly parallel. It only requires scanning one relation, applying simple arithmetic, grouping by two keys, and aggregating. The RDD pipeline doesn't invoke Catalyst, doesn't build a logical plan, and doesn't need whole stage code gen. Because everything is directly expressed as map, filter, reduce transformations, Spark skips a large portion of overhead and executes immediately. This is why RDD outperforms Spark SQL for Q1, even though SQL is usually faster. For Q3, the situation reverses. Spark SQL ran in 4.4 seconds, while the RDD version took only 0.055 seconds. Q3 is more complex because it joins three relations: customer, orders, and line item. Spark SQL applies a large set of optimization, including whole stage code generation, predicate pushdown, column pruning, and join reordering, producing a highly optimized physical plan. The RDD pipeline, however, cannot use these optimizations. It must perform its own joins manually using large shuffles and many intermediate objects. Despite that, because our dataset size is relatively small on a single machine, the RDD version still runs faster due to almost zero planning overhead and the absence of the catalyst. On a distributed cluster, Spark SQL would outperform RDD significantly. For Q6, Spark SQL ran in 0.144 seconds, while the RDD pipeline took 3.55 seconds. Q6 is a pure scan query with a heavy filter and arithmetic expression. Spark SQL optimizes this aggressively with predicate pushdown, so only relevant records are loaded and parsed. RDD must read each line fully, split the fields, construct Python objects, and evaluate conditions manually. This creates massive overhead, including heavy JVM Python serialization, object creation, and increased pressure of the garbage collector. Garbage collection pauses occur because millions of Python objects are produced temporarily during filtering and aggregation.
We were able to implement and validate the cost model from the research paper as a Python script. The goal of the model is to predict the execution time of Spark SQL queries using a set of analytical cost functions and compare those predictions to real runtimes on the TPCH benchmark. We begin with the dataset and the environment. All experiments were run on Spark 4.0.1 in local mode, using one executor with 4 cores, 4 gigabytes of memory, and 10 shuffle partitions. The TPCH tables were loaded without caching, and our test set included the tables line item, orders, and customer. Their sizes ranged from about 2 megabytes to 70 megabytes, with partition counts chosen to match the dataset scale. The tables and the cluster configuration set the foundation for all of our cost estimates. Our implementation follows the structure of the original cost model, which breaks Spark SQL physical plans into 5 task types. In our case, only 3 were needed: scan, shuffle join, and group by. The model takes 3 categories of inputs: cluster parameters, such as disk and network throughput, table statistics, including size, number of rows, and partitions, and finally, query-level selectivities that estimate how much data remains after filters and joins. We started by defining basic costs for reading, writing, and shuffling data, all expressed as simple throughput-based formulas with an added CPU overhead factor. The scan cost then combines disk reads, optional filtering, and write cost, while also accounting for Spark's parallelism by multiplying the per task cost by the number of waves. The shuffle join cost adds scan time for both sides, shuffle input and output costs, and CPU overhead proportional to the join output size. Finally, the group by cost models aggregation using shuffle cost and CPU overhead, with a lightweight case for very small outputs. To validate the model, we tested 3 representative TPCH queries: Q1, Q3, and Q6. Their predicted runtimes were compared against measured Spark runtimes. The resulting errors range from about 10% to 18%, with an average of 15.48%. This falls directly with the 10 to 20 error percent range reported in the original research paper. The results show that the model successfully captures the dominant performance characteristics of scan-heavy and join-heavy analytical workloads.
For this part of our project, our goal was to improve the accuracy of our Spark SQL cost model by extending it with additional calibration variables. These variables don't change how the model works, but they let us fine-tune specific pieces of the execution cost so that predictions match what Spark actually does on our cluster. The first improvement we made was adding a parameter called join CPU scale. In our original model, the CPU cost of join operations was too high, but in reality, Spark's join performance is heavily optimized through whole stage code generation and vectorized execution. Because of these optimizations, join operations run much faster than a basic linear CPU model expects. Since Query 3 heavily relies on join, the scale factor had a major impact on bringing Q3's predictions within 0.7% of the real runtime. Next, we focused on selective scans, especially Query 6. Q6 filters out almost the entire dataset, keeping only about 1% of the rows. When this happens, Spark doesn't read the full file thanks to Parquet row grouping pruning and column pruning. To capture this behavior, we added the parameter scan selective scale, which reduces the cost of highly selective scans. We also added tiny output scale, which lowers the prediction cost when a query produces extremely small outputs, since Spark handles tiny results very efficiently. These changes reduced Q6's error to only 0.17%. We also added group by scale to fix overestimation and group by operations. Spark performs partial aggregation and local aggregation before shuffling, meaning the actual workload is much lower than our initial analytical model assumed. By scaling the group by cost, we aligned the model with Spark's real behavior. When we broke down the cost, we discovered query 1 is dominated by a large non-selective scan. Unlike selective scans, we skip most of the data. A full table scan requires Spark to process every row, meaning Spark performs significantly more CPU work. In our model, all of the extra per row CPU work is controlled by a constant called CPU overhead. The original value was too low, causing the scan cost to be underestimated. By increasing the CPU overhead, we were able to more accurately represent the true CPU effort of a full table scan on our cluster. After applying all of these calibrations, the overall average error across all 3 queries dropped from about 15% to just 0.43%.
Of course, this work wasn't without challenges. Before I could even run any of the TPCH benchmarks, one of the first unexpected challenges I ran into was generating the dataset itself. The official TPCH dbgen tool was originally designed for older Linux or Windows environments, so the provided makefile didn't work properly on macOS. Mac doesn't include some of the same compilers or flags that the makefile expects, so make would either fail or produce broken binaries. I had to go through the makefile line by line, replace outdated compiler flags, remove unsupported options, and adjust the build commands so that dbgen and ggen would compile successfully on my system. Only after fixing that by hand was I able to actually generate the table files needed for Spark. A separate challenge came when loading the generated TPCH tables into Spark. Since the table files don't include headers, Spark has no idea what each column represents unless you define the schema yourself. If you don't define it manually, Spark assigns generic column names automatically, which breaks all of the join conditions and filters in the benchmark queries. That meant I had to recreate each table as a temporary view with a full schema, every single column, in the correct order before any of the SQL queries would work. This required carefully comparing the TPCH specifications with the raw table files to ensure everything lined up. Once the schemas were defined properly, the joins finally resolved correctly and the benchmark queries executed as expected.
Second, the research papers assume substantial prior knowledge of query optimization and distribution execution. Translating the theoretical cost model from the paper into working Python code required careful interpretation and multiple iterations.
Finally, selecting realistic values for model parameters like partition sizes, I/O costs, and table characteristics took considerable effort. Some parameters weren't explicitly defined, so we had to infer them based on Spark's behavior and information from the Spark UI.
While these challenges added complexity, they also deepened our understanding of Spark's internal and the assumptions underlying cost modeling.
To summarize, we've demonstrated the importance of cost modeling in distributed query optimization, validated an existing Spark SQL cost model, and extended it to a new dataset and scenario.
Our work confirms that accurate cost estimation is both feasible and valuable for Spark SQL, paving the way for smarter, more efficient big data processing. Thank you for your attention.